All right, I gave you a homework assignment. This homework assignment, I think I have it set to be due on something like January 29th. I don't know. Something like that. This is actually, I had a physics major who took electricity and magnetism at UNL. And the first day of class, they were given this assignment as a review assignment for what they should have learned in their in their introductory level class, the one you're in 252. And so I'm giving you the same assignment they had. If that's what they should have learned, it's a review assignment for them. It seems like it's a good assignment to make sure you got through it. Now, some of these problems, after today, you'll be able to approach. Some of them you won't. So don't sit down and say, I should do this whole thing tonight. But you should be able to do like 3 of them based on today's lecture. Now, are we going to cover everything you need for those 3? Are you going to be comfortable? Maybe, maybe not. Please feel free to come contact me for help. Something I want to point out here just to make sure that credit is fully received is you have things like draw a sketch, use a ruler. I want to see sketches with very careful straight lines, not just rough pictures. And there is a rubric. If you look on Moodle, there's a rubric for the points, how they're going to be distributed, so you can get an idea of what I'm looking for to make sure you have these. Semi-infinite wire is a wire that has a starting point but no end. So it's a ray if you want to use the terminology from geometry. And you're going to find the electric field due to charge on the wire. 2 different things. Electric dipole, this one you won't be able to do. Actually, you could do that already probably, but yeah, that one's not a significant one in terms of the difficulty. Charged non-conducting sphere. Yeah, life's getting more interesting. You can't do this one yet. That one you'll have to wait at least another week before you can even start it. Likewise, this one here, you'll have to wait at least another week before you can start it. This one here is actually real simple, but we have to get to the law, so you won't be able to do it yet. Yep, have to wait on that one. And have to wait on that one. It's just the 2 that you can do after today's lecture. Just making sure you have some understanding of what's going on. And like I said, if you have questions, come talk to me. These are not simple problems. Yeah, when you get it all done, you might decide, oh, that was easier than I thought. But they're not simple. And it's going to take some interesting calculus work to make it so it comes out right. And I have to be honest here in my assessment as we go through today's lecture. I did not review that interesting calculus work that I'm going to have to do in today's lecture. Yeah.
So some of these problems you'll be able to do by today, right?
Just the 1 and 2.
Just 1 and 2.
Yeah. The others will be a different way. So we're going to study today Coulomb's law, and notice it has the subtext of integral form. So we're going to look at Coulomb's law, but we're going to look at a calculus form. So here is Coulomb's law. There I wrote out his name. I said in class, 4 times. I say Charles Augustin de Coulomb. He came up with this inverse square law. We call it inverse square law because the force is inversely proportional to the square of the separation. There's one thing missing in my equation. Force is a vector, and remember it's important to put vector signs over vectors. Or you can make it in bold, and I could just pretend that I had it bold there and pretend I was right, but that's not the case. This is a vector equation. It has direction. In general physics, I told you, use your brain for the direction and just calculate the magnitude. We're going to do things pretty similar to that in calculus as well. We're going to break things into components and then do the components so it's a little different. It's not just finding the magnitude and doing the direction, but it's similar. Now, one thing I need to point out, this is not a calculus equation, right? So that's not our ending point. This equation works for static charge, that is stationary charge, if you have 2 point charges, 2 charges of 0 volume. Well, how often do you have a charge of 0 volume? Never. Now, we can approximate it to be true if we're far away from a point charge compared to its size, but that's an approximation. Now, in real life, we usually have charge distributed over a range. If it's distributed over a range, well, I showed you in class yesterday, if you had 3 point charges, you just say, well, I have this force between this pair and this force between this pair, and then I add up the vectors. So that's what we do with calculus if we have a continuous distribution. We have to break our charge up into an infinite number of infinitesimal pieces and then calculate the force vector from each of those pieces and add the vectors up. So that's what our method is going to be. Now, before I go further, remember I didn't write the constant in class yesterday. I had to go on memory. Unfortunately, I was correct. The technical constant is this right here. So K is 1 over 4 pi epsilon 0. Epsilon 0 is called the permittivity of free space. That is a parameter that tells us how easy it is to pass charge through a vacuum. And so K is just based on that. So you'll see some textbooks that don't use K at all. K is often called the Coulomb constant. Since K is built on epsilon 0, which is considered a universal constant, they often will just write it the way I did here without the K. Here I wrote K with the subscript of E to make sure we're clear. It's the Coulomb constant, not any of the other Ks we use. Because we have the Boltzmann constant that's also K. And so sometimes I'll use K sub B for Boltzmann, K sub E for the Coulomb constant.
And this is the 8.99.
Yes. Yes. The next slide has the actual value. It has the values both of the permittivity of free space is right there, and the K value is at the bottom. And of course, you don't have to, Chad, you don't know this because you weren't in the class last semester. I basically don't require you to memorize anything. I will give you all the constants and all of the equations for tests, but of course, you do have to know what the equations mean and how to use them. So you don't have to know these numbers. You don't have to know that epsilon sub 0 stands for the permittivity of free space, but you do need to be able to use them. All right, so how do we use this? I decided not to use the PowerPoint presentation, so the fixes I was doing when you came to my office, Chad, were rendered moot since I'm not using the PowerPoint. So using Coulomb's law. First, because we're going to be dealing with a distribution of charge, we have to add up all the forces, which means an integral. So we actually will have df, and once again, I should have put a vector over it. df vector is minus keq1 r unit vector over r squared dq, or minus keq1 r over r cubed dq. Once again, my vector sign, I do remember what happened. It was a change in Microsoft Office that made those vector signs disappear. Yes, Nate?
So are we talking about like two, pretty much just two objects of charges?
No, this is for dealing with a, let's say I have a point charge here, and I have an object like this little, it's called a tombstone, that has charge spread over it. And I want to find the force on this charge due to the charge spread over the tombstone. And so our dq is going to be each little bit of charge on this tombstone we're going to have to integrate over the tombstone.
Over the surface area or back there?
If it's a conductor, the charge is only on the surface, so it's the surface area. If it's an insulator, the charge will be spread throughout and you have to integrate over the entire volume.
Okay.
So, good question. In fact, I think my next slide is going to deal with that. Now, if you look at the homework does not ask you to find a force. It asks you to find an electric field. And this is the point where I'm just going to introduce what an electric field means, because it's a simple concept, that has a lot of ramifications. So we already talk about force fields. We talked about force fields all first semester, but I don't think I ever said force field. And if you watch sci-fi, they talk about force fields, right? Well, here's the force field we have talked about. What do we normally call that? We called it the acceleration of gravity. Not just gravity, because gravity is the name of the force. But that's the gravitational force field. The acceleration of gravity is the gravitational force field. What does it mean for it to be a force field? The force field is defined as the force divided by the charge associated with that force. So the charge associated with the gravitational force is mass. So if I want to take the Earth and I want to calculate the force field due to gravity from the Earth, I'm going to take the force of gravity acting on an object at some location divided by the mass of that object, not divided by the Earth, because I'm finding the force field caused by the Earth. So I'm not dividing by the mass of the Earth, I'm dividing by the mass of the other object. And that gives me the acceleration of gravity, the gravitational force field. It has a direction. Remember, the force of gravity is always down. That's how we define down. So that's a gravitational force field. How do we use that gravitational force field? Well, we just take that same equation and we say, given some mass m, the force on that mass m is the mass times the force field. It's the charge times the force field. But remember, the charge for force of gravity is the mass. So we're going to take that same idea and apply it to electricity. So if I have the example I was using here with Nathan's question, if I have a point charge here and I have charge spread out over this tombstone, I want to find the force field that's out here where this point charge is. So how would I find the force field due to the electric force based on that object? By the way, we call the electric field capital E. So the electric force field is equal to, what should it be? Looking at the gravitational force as your guide.
Force is about the current? Is that what's going to be current about?
Not current, but the electric force.
Okay.
Then what? Over the charge. The electric charge, because that's the charge associated with the electric force. So that's the definition. Remember, if I put the 3 lines, that means definition. That's the definition of the electric field. It's the force per unit charge, just like the gravitational field was the force per unit mass. So I have this equation here for the force. That is the force on my object here based on the distribution of charge over there. I can write this in terms of electric field. By the way, just to complete this, this is why we use electric fields, because the force can be calculated on any charge by taking the electric field multiplying by that charge. But then I can say that the dielectric field is d force electric over Q. And I've got the d force electric there. And so there's the equation for the dE, the electric field produced by some small piece of charge dQ. Yes?
You maybe answer this, but like what are the units? Like, what is?
Okay, what are the units?
What is FE and what is Q? Do I need to?
Okay, those are good. Those are good. So Q is charge. Charge has the units of Coulomb. And so that means that the electric field, it's F over Q. Force is newtons. Q is Coulomb, so it's newtons per Coulomb. So electric field is in units of newtons per Coulomb.
That's the unit for electric field.
Yes.
So I have a question. So when you say point charge,
Yes.
do you mean just a charge that's charged by itself? Is that here?
Yeah, we will actually move to just saying a test charge. A test charge means it's not necessarily even there. But if I were to put one here, what would happen? And so it means I have a charge at this specific point.
So it doesn't have this object really?
No, that's correct. A point charge has no volume. It's just at a point.
Is there any such thing?
No, of course not. Hey, don't demean physics here. All right, so what do we have here? We have an equation to calculate the force or the electric field once we integrate it up. I should make sure, I know I mentioned this kind of in passing, make sure you recognize that these are exactly the same thing. Since R hat by definition, oops, that's not a hat. R hat by definition is equal to R vector divided by R. That's all that's been done to change those two equations. Is substituting that R hat is equal to R vector over R. Sometimes it's easier one way, sometimes it's easier the other, so I just wrote both ways. Depends on what your problem is, how you're going to want to solve it. So, this is our equation. What should I do for the rest of the class period? I should practice using it. Yes, examples. So, first, how we go about doing it. Here I have bold F that's clear, so you know I have the vector correctly there. To add up all the force vectors, we must integrate dF as a vector. And we do that by breaking into components. So as I go through doing problems, I'll say, okay, here's my, and I have to define what X and Y directions are. Here's my magnitude of dF. Here's the component in the X direction. Here's the component in the Y direction. And I go from there. So I will make two integrals, one for the X component and one for the Y component. This goes to a question that Michael asked. He asked, just over the surface or is it over the volume? And it's going to depend on your problem. So I have three variations here for what dq is. dq is a small piece of charge. If you have a one-dimensional problem, i.e. I have a wire, then my dq is just going to be the charge per unit length multiplied by dl, the little piece of length. And so that's the first line. dq is lambda, the charge per unit length. Okay, there I put ds for a little piece of length. Lambda could be something that changes or something that's constant. You pray that on the test, lambda or sigma, oh, actually I have mu here, excuse me. Lambda or mu or rho are constants because it makes life easier when you're doing integrals. But it may be that it's constant and it may be that it changes. You have to know, right? So the problem's going to have to give you some information there. You can't just, go on out limb. If you have it over a surface, like I said, if it's a conductor, then the charge is over the surface, and then dq is, I put mu here. I think I should have put sigma, but the charge per unit area, also known as the areal charge density, times dA. So what is dA? Chad, you've already taken a lot of calc, right? Or what's your calculus status?
Up to 3.
Okay. So yeah, that's a lot of calc. Just, for comparison, most people have taken calculus up to -5 or so. So dA means that you're going to have two d's here, actually. In Cartesian coordinates, dA is dx dy. If you have something more complicated, it may be more complicated. And then for three-dimensional, we have rho, the volumetric charge density, times dV. And if it's dV, that's 3 dimensions. So in Cartesian coordinates, dx times dy times dz. In spherical coordinates, as was going over with Chad this morning. We have r squared sine theta dr d theta d phi. So there can be some complicating factors there. So you have to start by considering the geometry and what the appropriate dq is. You can't just jump into a problem without considering the geometry. And we will learn next week about Gauss's law. Gauss's law is easier if you have an exploitable symmetry. And so we'll learn about that next week. A second way to do this that's easier in some cases. Break your DF into components and then solve them independently. So let's get to work. Consider the force on a point charge Q1 due to charge Q2 evenly distributed over a wire of length L shaped in a circular arc of radius R about charge Q1. What's the first thing you should do if you're doing this on a test? Chad hasn't taken one of my tests yet. You will have for the last 3 problems. If you answer them all right, it's all fine and dandy. If you don't, then I will grade by partial credit. And the first 2 points are, did you draw an appropriate figure to help you solve the problem? So you want to get used to that. In physics, we consider that very important because once you can visualize the problem, it's a lot easier. So the first step, draw the figure. So of course, I wrote this question. I kind of know what the shape's going to look like, but I have a circular arc. So I'm going to start with, there's my circle of radius R. And I have charge Q2 that's evenly distributed over that. So that means that I'm going to have, is this a one-dimensional distribution of charge, a two-dimensional distribution, or a three-dimensional distribution?
If it's on the wire, then that means it will be one dimension.
One dimension, that's right. So one dimension because it only has the ds, the change in position on the wire, basically. And so I'm going to choose to draw a little piece of wire here of length ds, and it's going to have charge dq is equal to the charge per unit length. Well, that wire has a total charge of q2 divided by the entire length. Well, what's the length of a circle? It's 2 pi r. And then I have to multiply it by ds. So I've determined what my dq is. And notice that is a colon between the ds and the dq, not an equal sign. Otherwise, you'd have nonsense, mathematical gibberish. So I've determined what the dq is. The next step is, where am I going to find the force? Where is charge Q1? It's at the center. So I have Q1 is at the center. And now I want to find the force on Q1 due to that charge. What should I do now? I'll help you out as you're thinking. There's a long answer and a short answer. I will tell you the short answer at the end if that's not what you choose.
I actually have a question.
Go ahead.
I understand why, okay, I know I don't. But why is Q1 in the center?
Because it says of radius r about.
Yeah, I got that part, but isn't Q1, so Q1 in the center is the charge of this wire.
Could you explain what Q2 is again?
Okay, Q2 is the magnitude of charge that is on the circle. Q1 is the magnitude of charge that's at a point at the center of the circle.
So that's a.
So why is it?
No, it's not.
Why is it over the circumference?
Why is it what?
So,
Because the problem says evenly distributed over a wire of length L.
okay, so, right, and then times the infinitesimal lengths on
Yeah,
wire.
the DQ is the charge per total length divided by the infinitesimal length. And I over-specified, I have L and R. L is equal to 2 pi R, so I didn't need to specify L. I'm looking for the force on the point charge Q1. So what should I do?
So that would be the force of the charge on the wire on Q1.
Right.
Okay, so it would be, you would take you take into account the distance.
Okay, take into account the distance. Let me write down the equation for you. We have dF.
And then it'd be a change as it goes around the circle.
I put over capital R squared because it's constant radius.
I mean, radius would be constant.
Because I'm at the center of the circle, yes.
I forgot, our hat is what again?
R hat is the unit vector that's pointing from A to B. In this case, it's the unit vector pointing out.
From Q1?
Yeah.
Okay.
From Q1 to where DQ is. Is that right? Pointing out? If they're both positive, it's repulsive. Yeah. What should I do next, gentlemen? If anyone at any time sees the short answer, just blurt it out. We're going to do it the long way, whether you do or not. But let me back up to the steps. We have determined DQ. We considered the geometry for appropriate choice. Sure, we did. Now what do we need to do? We need to break into components. So I will define two component directions. One that is like that and one like that. Call that X, call that Y. And I'm going to define an angle. I'll call it theta there. And so in that case, then I need to write ds in terms of theta. Right? I had ds up there. If I'm using theta, what's the relationship between the arc length and the angle? S is the arc length. If it's not coming to you, it's not going to come to you. S is equal to theta r. That's the definition of the arc length. So for a complete circle, theta for a complete circle is 2 pi. Hence, the circumference of a complete circle is 2 pi r. So given that we have a constant radius, ds is just equal to r d theta. So I'm going to make that substitution. Forgot the Q2.
that we would eventually substitute DQ for what was there.
Yeah.
With that modification.
So here I've rewritten this. Notice this is a Q2, not a theta 2 at the end.
Okay, that's what I'm saying.
But we have the R hat, and this says break it into components. So how do I find the components in the X and Y direction here?
You try to separate theta and R.
Well, if I have, here's df and here's theta, then how big is dfx?
It would be
Is it 0?
Well, I have some angle theta there. It's not always
Oh,
0.
okay, no, I was thinking about that backwards.
it would be tangent theta.
We want to relate the adjacent side and the opposite side.
So it'd be some sort of reduced, right?
Adjacent over hypotenuse.
No, yeah, adjacent over reduced.
Opposite or adjacent?
No, yeah, it's
For dfx, opposite is
and then that
dfy.
would be cosine.
So that's cosine. That's right.
Yes, then it'd be cosine times would be times df, I believe, right?
Yes. Notice I had r on top and r cubed on bottom, so it came back to over r squared. So there's my dfx. And likewise, I'll have dfy. The y component is going to be the opposite side. Opposite over hypotenuse is sine. So now I'm ready to integrate. What's my variation? Oh, I forgot to put Q in both of those. This Q2 here disappeared. My bad. I'm just going to put it in black. That way no one will ever know that I forgot it. Well, that's not black. That's black. There. No one will ever know. What's the variable of integration?
So the thing changing is the angle.
The only thing changing is the angle, theta.
So with respect to theta, and then radius is a constant.
Yep. What's the integral of cosine theta d theta from 0 to 2 pi?
Okay, so are we integrating what's on the bottom left? No, bottom right.
Well, we have to do both the red one and the green one. We have to do both the x and the y.
Okay.
So I've run out of page on this slide. I hate to add another slide for this, but I will.
It'd be nice. It'd be sine.
Negative sine of, what were the equals you gave?
What was that? Chat. What was that?
I asked what angles you gave, because you gave angles, and I just.
Oh, it's doing a complete circle, so it's
Okay,
0
so
to 2 pi.
0 to 2 pi. So negative sine is 0, negative sine 2 pi.
Oh yeah, we're gonna try and follow this, right?
I'm hoping I remember this correctly. Go back to see if I did that. Yeah. So if I do this, notice this stuff here is a constant.
So it's simply nice cosine in that case. Yep. Here's the part where
I erased sine and wrote sine again there. That's how genius minds work. Okay, flawed minds work. So I basically have to integrate cosine theta d theta over one cycle. What's the integral of cosine theta d theta over one cycle?
So the integral would be sine.
The integral of cosine will be sine.
And then you put in the substitution.
So I'd have sine of 2 pi minus sine of 0.
So sine of 2 pi. Sine is it it's vertical, so it'd be 0.
It's 0 minus 0.
So yeah, 0 minus 0.
We didn't have to go, right, you guys have learned a lot of calculus and you want to just do the calculus. But at this point in life, it's time to start thinking a little deeper. Think about what it means. A cosine curve goes like this, right? And over a complete cycle, and I'll write it on here instead of writing in space. Over one cycle, the cosine curve goes like this. And what does it mean to do the integral? You find the area under the curve. And so we're adding up, that's positive, and this is negative. And what am I going to get when I add those all up? 0. Yep. So we didn't have to go through, the integral of cosine is sine theta d theta is sine theta, if we think about what it means to do the integral. And you'll find, just like last semester when we did the Gaussian integrals, oftentimes we will do things where we think about it a little more and do a little less math because we thought about it. So the answer there was 0. Force in the x direction is 0. Now let's go ahead and do the y direction.
I believe that one has the sine.
Yes. This time I'm putting the constants outside the integral right off the bat. And what am I going to get for this integral? And which gives us?
That should be minus 1 minus 1. Pretty sure.
Just doing the same thought part as we did before. There's my sine curve going from 0 to 2 pi. Doing that integral is going to have to give us 0. So now we found the net force in the x direction is 0, the net force in the y direction is 0. So what's the net force here? Yes. Doesn't matter if I put a vector sign or not because it's equal to 0. The short answer would have been for somebody to blurt out right at the beginning, 0. But once again, how would you do that? And this is actually an important part of physics, is recognizing these things. You would do that by looking at the symmetry. For every piece of wire that you have above, you have an exact piece of wire down below. And so you're going to have a force vector that's, well, assuming they're both positive, that's pushing down from the top. Force vector from the bottom is pushing up with equal magnitude. You go around a circle, it was all added to 0. It had to be 0 based on symmetry. So in physics, oftentimes we will analyze the symmetry and just say, based on the symmetry, it has to be 0. Sometimes it'll be based on the symmetry, it's twice what I get if I go from here to here. But we make these symmetry arguments to simplify our math lives. Because math is a very, very important tool, but in terms of physicists, we view math as a tool. And we want to make it as simple as we can, not, let's do a hard problem.
So what are the other symmetries that are not zero, like the net force?
Well, let's go to the next problem. Yeah, there are plenty of those. You wish you got all the zeros. So the next one. Consider the force on a point charge Q due to charge Q to evenly distribute over straight. Okay, actually I wanted to do a variation on the problem we just did. I thought I had that next, but apparently not. So here's the variation on the problem we just did. Same loop. Okay, I made it blue instead of black. Let me fix that. Same loop. Same charge Q2 over the entire thing. But now I'm going to put a point P that's some distance A from the center of the circle. That's not a P. That's a P. And I want to find the force at point P. If we look at our symmetry, we now say, uh-oh, I can tell you that the parts that are vertical, up and down, and going in and out of my page are going to be 0 based on symmetry. Because if I look at, let's take a little piece of the wire here, ds with dq, and I'll stay with the same thing we had before, q2 over 2 pi r ds equals q2 times, Did I make a mistake with my r's? Over 2 pi r. Yeah, no, I didn't. Okay. I just get worried. I don't like mistakes. After class, if I find I made a mistake, I'm really embarrassed. It's better to correct it during class. Okay, so from that little ds, we have dq is this red. That's going to make a force vector. If q2 is positive and q1 is positive, I'm just going to choose my signs based on them both being positive. If one's negative, it's going to reverse the direction. If both are negative, it'll bring it back. So I make my arrows based on them both being positive. I would have a repulsive force. So that's the direction df would be pointing from that little ds. But I know that based on symmetry, if I were to choose a piece down here, it would make a df like that. And if I were to add those two df's together, what would I find? 0 in the vertical direction, but not in the horizontal direction. So I have to choose now a 3-dimensional coordinate system, not just a 2-dimensional coordinate system. And I'll go ahead and call this X, Y, and Z. So my Z direction now is what my Y direction was before. Actually, it would have been smarter for me to do it. We typically do it like this. Just to make sure you understand, this is just a little piece of arcane math. When you make a coordinate system, we always say a right-hand coordinate system. That means that it follows the right-hand rule, which means that X cross Y is equal to Z. So I need to make it so if I take my index finger, I point my index finger in the direction of X, my middle finger in the direction of Y, my thumb points in the direction of Z. That's what makes a right-hand coordinate system. Have you heard the term right-hand coordinate system before? Hopefully you have. That's what it means. Okay, so I have a right-hand coordinate system, and so all I have to worry about here is, well, what's this angle? Let's call this angle alpha. Which part of my force is not going to come out to 0? By symmetry, we can say 2 of the components come out to 0. Which one doesn't come out to 0? The Z. So all I need to do is find what dfz is. I don't need to find dfx or dfy because by symmetry arguments, I can say dfx and dfy are 0. So dfz is going to be equal to the magnitude of df times cosine of alpha. Alpha is a constant for this problem because I'm a distance lowercase a away from the center of the circle, and the wire is always going to be a distance capital R away from the center of the circle. So alpha, I can immediately say cosine alpha is equal to adjacent, which is A, over the hypotenuse, which is the square root of R squared plus A squared. So that's just a constant. Michael, what was that?
How did you get it?
How did I get that?
Yes.
I got that from, I will redraw the triangle. I got it from the triangle alpha there. That's this alpha. Can you see where my pointer is?
Yes.
Okay. And then this side here, I knew was R. This side here, I knew was A. And then I used the Pythagorean theorem. Yeah. And that's a good question, Michael. I went straight to it, and I should have shown you this triangle first to make sure it was clear. So now I just need to find what df is again and integrate. So what's df? Minus ke, and then I'm going to have the dq, which is, notice these r's actually cancel in the dq. All over, and now this is going to be the distance from point P to the wire, which is that same hypotenuse squared. So on the bottom, I have the square root of R squared plus A squared, quantity squared. Let me make it clear. The hypotenuse is the thing in parentheses, and then I squared it. So there's df. If I want dfz, I just have to multiply that by cosine alpha, which is that constant there. So there I've rewritten what's above, and I have to add the additional times cosine alpha. So there's the cosine alpha.
So, can you say why df of z is equal to, go up, was it equal to df times cosine?
Yes, the z component is the amount that's coming out in this direction. The length of this vector is df. And so the component that's in this direction is going to be the adjacent part of a right triangle right here. Chad, what was your question?
Can you explain how you got from like the basic formula of df to that df? Like obviously, like,
Okay, how I got to this equation right here.
Yeah,
right?
just mainly the r hat and dq. Like, how did that turn into?
Okay, so the r hat disappeared when I did this right here. That's where the r hat disappeared, right? Because I took the magnitude of df, which means I drop r hat, and then multiply it by cosine alpha to get how much is in the z direction. So if you prefer, I could have put magnitude sign there to say, yes, r hat disappeared. Okay, so then let's come back to our equation all the way back here. So I'm using this right here. Oh, and you know what I did wrong in both problems I've done today? I did the electric field instead of the force. The difference in the electric field and the force is the inclusion of Q1. I forgot to write Q1 in both the first problem and the second problem. I can retroactively fix that by putting this on each one. But that was obviously a mistake to forget. So I'm changing all of these because, you know what, I'm just more comfortable doing the electric fields. But it's important to recognize, yeah, you got to pay attention. I made a mistake. I'm not using the same colors I had the first time because I actually think it's only fair for my mistakes to be visible. Okay, I see your hand, but I'm out of time, so I'm going to finish this question, then I'll come to you, and then we'll stop. So then my DQ, I had calculated and plugged that in. So that's where the Q2 times, the R's canceled. So it was Q2 times d theta over 2 pi came from. And then the R squared stayed on bottom as R squared. So that was the process of making this equation here. And remember, it should have had a Q1 on top for it to be force. Divide out that Q1 on top and you have electric field. Okay, what was your question before we?
Just answered it with that.
Okay, so the answer, to finish this, you just integrate theta from 0 to 2 pi. So it's just going to be Fz is equal to minus Ke Q2 A over 2 pi we have that square root now cubed multiplied by 2 pi for the integral. Those 2 pi's cancel. And we have that. So here is an example, Michael, where the symmetry did not make it come to 0. It did make 2 of the compounds come to 0, but the third one didn't. I thought you were wearing sunglasses. I guess it's just bright outside. Thought Michael's too cool for school these days. All right. Any questions before we leave? All right. Have a great half-hour break at least. That's what I got. And I'll see you either in a half hour